Assalamu alaikum, my dear students. As you know, in our previous lectures, the learning outcomes which we have completed, number one was solution. In solutions, we have two parts. One is concentration and another is the colligative properties. In concentration, we were discussing about molality, mole fraction, normality, parts per million, parts per billion, parts per trillion, parts per quadrillion, mass percentage. So we have already discussed a lot of examples related to this topic. Then we were discussing about colligative properties, the second part of the first chapter. So colligative properties are four properties: relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. So we have done it successfully. The second learning outcome was, if you remember, it was related to chemical kinetics. So we have also explained it, what is molecularity, what is order of reaction. Then we were discussing about the initial rate law. If we have given experimental data, how to calculate rate law expression by using initial rate law method, how to calculate order of reaction, overall order of reaction, and how to calculate rate constant. Now I am going to discuss today new chapter, that is chemical equilibrium. What is chemical equilibrium? It is when the reaction has two spots. It is a forward reaction. If the forward reaction and backward reaction are occurring at the same rate, then we are saying the reaction is in chemical equilibrium. So chemical equilibrium occurs, you can say like this. Chemical equilibrium occurs when a forward reaction and it is reverse reaction. Chemical equilibrium occurs when a forward reaction and it is reverse reaction are taking place at the same rate. So here we have forward reaction and reverse reaction when they are coming at the same rate. So for example, let me give you one example. So if we have N2O4 dinitrogen tetraoxide, so this is forward reaction, it will give twice NO2. We are saying this is forward reaction. But if conversion of twice NO2 to N2O4 will also come at the same speed, then we are saying this is reverse reaction. So this reaction will be forward reaction and this will be reverse reaction. So in general, if I give a general reaction, general equation, we are giving like this: AA plus BB gives CC plus DD. If I have to give equilibrium constant for this reaction, I will give like this: concentration of A to the power A, product divided by reactant. It is equal to product is divided by reactant. You know this side is product, this side is reactant. So we can say CC to the power C, DD to the power D divided by AA to the power A, BB to the power B. This is the general reaction. Now if I will show you this principle, how to apply this rule in this equation, and how we are showing forward reaction and backward reaction, then we have some chemical reactions examples and we have to give equilibrium constant expression. So let us do so. Let us apply this rule in this example. So let me show you N2O4 it will give, it is in gaseous state, it will give twice NO2 gas. So this is forward reaction. If it is forward reaction, what will be the rate of forward reaction? Rate of forward reaction is equal to Kf. What is K? Equilibrium constant. F means forward reaction. So equilibrium constant of forward reaction. So it will be N2O4. You know, rated directly proportional to reactants. Now second step. Step number 1, step number 2. If we will go for now reverse reaction, so twice NO2 gas, it will give N2O4 gas. So this is reverse reaction. If I have to give rate of reverse reaction, I will give K R N2 NO2 because directly proportional to reactants. NO2 का whole square. Now at equilibrium, rate of forward reaction, if I write here F, here I will write R. Rate of forward reaction is equal to rate of reverse reaction. When this rate of forward reaction is equal to rate of reverse reaction, it means then this and this will be also equal. So we can say Kf N2O4 is equal to Kr NO2 ka whole square. Now if I want to take some another write it in another way, this Kf divided by Kr, it will be equal to this Kf divided by K, it will be equal to NO2 ka whole square. Let me write it properly. Divided by N2O4. Now instead of equilibrium constant for forward reaction, equilibrium constant for reverse reaction, if I write a general equilibrium constant, how I can show it? I can show instead of this Kf and Kr, I will write K equilibrium. It means the Kf over Kr is equal to K equilibrium constant. So let me show it here. We will say Kf and Kr is equal to K equilibrium constant. So it will be equal to NO2 ka whole square over N2O4. This is our final equation which we are saying equilibrium rate expression. So from this you can say equilibrium constant is directly proportional to products. So from this you can say equilibrium concentration is inversely proportional to reactant. Okay, this is our conclusion from the equilibrium constant. Now if I do some practice problems, suppose practice problem we have some chemical equation, we have to show it is equilibrium rate expression, how we can show. But remember one thing, for solids and liquids there is no activity. It is this equilibrium constant is applicable only in gaseous state. So if we have now these these problems, these chemical equations, we have to give equilibrium rate expression. So we have to show in terms of equilibrium constant how we can show them. So let me solve some examples. For example, if I give solution of this equation, before giving solution you have to keep in mind for solids and liquids, they are not involved in K equilibrium equation. In K equilibrium, you have to keep in mind solids and liquids are not involved in K equilibrium. Only gases. So what we can say? Only gaseous molecules, gaseous and aqueous. So now let us apply this concept here. If you see, this is solid, this is solid, so we don't have to care about this, they will not be involved in our equation. So we will give now K equilibrium. It is equal to product over reactant. So what is product here? 2 times carbon dioxide divided by carbon monoxide का square. So this is in gaseous form, this is also in gaseous form. So this will be our equation. So it will not be involved and this will not be involved. Now if I want to know the solution of this equation, what will be the K equilibrium? K equilibrium will be, if you see this is solid, so it will not be involved, this is solid, it will not be involved, only this one, so it will be equal to like this. So similarly, now if I solve this one, K equilibrium, this is solid, not involved, this is solid, not involved, only aqueous. So product divided by reactant. Product is zinc 2 positive, aqueous, divided by copper 2 positive, aqueous. This is the expression. Similarly, you have to figure out this and this. This is the homework, practice problems. So in the next lecture, we will give the relation between Kp, equilibrium constant at pressure P, equilibrium constant at concentration C, what is their relation, and then we will discuss some more examples related to this chemical equilibrium. Thank you.